Very good afternoon, students.
Good afternoon, sir.
Good afternoon, all of you. Last class, if you remember, we have discussed about the methods of preparations of alkanes like reduction, Kolb's reaction, and all. So today we are going to continue with the discussion. Wood's reaction we have discussed. Kolb's reaction we are going to do now. Kolb's electrolysis and decarboxylation, different other reactions and everything. So from carboxylic acids, we can actually prepare respect to alkanes by using two ways like Kolb's electrolysis and mainly decarboxylation. So what is Kolb's electrolysis? On electrolysis of sodium or potassium salts of carboxylic acid, generally alkane is obtained as a product. So what is electrolysis, students? We have a beaker or container where we have placed two electrodes. Yes or no? Where we are placing two electrodes, two metallic electrodes have been placed in a solution, to in a solution of electrolyte. Like what is the electrolyte now? Sodium or potassium salt of carboxylic acid. That means we have RC double bond O minus and Na plus, and we are adding this particular electrolyte to a solution where we have placed two metallic electrodes and we are connecting the external power supply to that particular system. Now current is entering the electrolytic solution. The electrode through which current leaves the electrolytic solution, the electrode through which current enters the electrolytic solution, that is anode, and the electrode through which current leaves the electrolytic solution is cathode. If current is entering the solution in this electrode or through this electrode, so electrons are moving away. Electrons are moving away from this electrode means that will be positively charged, which is said to be anode. And current is moving away from this electrode means electrons are coming into. Electrons are coming into means this electrode should be cathode. So cathode is negatively charged, anode is positively charged. At anode, what happens? Oxidation occurs. That means negatively charged species come into. So what is negatively charged species? RC double bond O minus. RC double bond O minus. At anode always oxidation occurs. That means loss of electrons occurs. So RC double bond O minus will undergo loss of electron to form RC double bond O dot plus an electron. If you take one more molecule, RC double bond O minus will form RC double bond O dot plus one more electron. Ultimately, you will get two molecules of RC double bond O minus. That is, two carboxylate ions will form two RC double bond O dot plus two electrons are released out. 2 RC double bond O minus gives 2 RC double bond O dot plus 2 electrons are released out. And RC double bond O dot, if you look at this carbon alkyl group, that is carbon-carbon bond in the alkyl group, this you can imagine as 2 electrons. This will also cleave homolytically. The homolytic cleavage will give the free radicals. You will get R dot plus C double bond O, C double bond O. Carbon dioxide is evolved. At anode, carbon dioxide is evolved and a alkyl radical is obtained. That alkyl radical will combine with each other to form RR, which is nothing but alkane. Alkane is obtained. At cathode, what happens? At a cathode, what happens, students? At a cathode, at anode, we have seen the formation of respective alkane and CO2. At cathode, whatever the electrons lost here, the two electrons, they have to be taken by the species. At cathode we have H2O. H2O will take up the electrons. H2O is nothing but H plus and OH minus ions. H plus will take up the electron to form H2 gas. H2O has two hydrogen atoms. Like you can take 2H2O, 2H2O plus 2 electrons will form 2OH minus, 2OH minus, or you can simply write the reaction in this manner. H2O is giving H plus and OH minus. H plus plus OH minus plus electron is giving hydrogen atom plus OH minus. So if you take 2H plus plus 2OH minus plus 2 electrons, it gives two hydrogen atoms will form H2 gas and 2OH minus. This equation is 2H2O plus 2 electrons gives 2OH minus plus H2 gas. So H2 gas is evolved at cathode. Along with the H2 gas, we have OH minus ions. This OH minus ions will develop electrostatic force of attraction with Na plus. Therefore, NaOH and H2, these are the products at cathode. And at anode, CO2 and alkane. At anode, alkane and CO2 is obtained. At cathode, NaOH and H2. At a cathode, we are forming a base NaOH. That means the pH of the solution has been increased or not? pH of the solution will be increased because base is formed. Everyone got these points or not?
Yes.
Yes, sir.
Right? So Kolb's electrolysis on electrolysis of sodium or potassium salt of carboxylic acid, generally alkane is obtained as product. If you do the electrolysis, you will get the alkane and carbon dioxide at cathode, at anode, and at cathode you had H2 gas and NaOH. So mechanism is same, whatever I have discussed. At anode, you have 2 moles of carboxylate undergoes loss of 2 electrons to form 2 RC double bond O dot. They will form 2 R dot and 2 CO2. This R dot will combine with each other to form respective alkane of higher number of carbon atoms. And at cathode, you will have 2 H2O plus 2 electrons undergoing loss, like 2 OH minus and 2 H dot is obtained. 2 H dot will be combining with each other to form H2 gas, to form respective H2 gas. Yes or no? The same thing you can see with the animation also. So CO2 gas at evolved at a cathode, H2 gas evolved at CO2 gas evolved at anode, H2 gas evolved at cathode, and alkane is formed at anode, and along with the H2 gas, NaOH is formed at cathode. Note, due to increase in the concentration of OH minus, the pH of the solution increases with the time due to electrolysis, because as we are doing electrolysis, more and more amount of OH minus is obtained. Because of more and more amount of OH minus, the pH of the solution has to be increased. And can we prepare methane by this method? Simplest alkane. Methane cannot be prepared because the two alkyl radicals has to combine. So simplest alkane which can be prepared is ethane. H2 gas is released at cathode and CO2 gas is released at anode. The same points, right, students? Look at the examples, you'll get clarity. CH3 C double bond O minus Na plus upon electrolysis forms what type of products?
Ethane.
CH3 dot you will get, because the CO2 is evolved. See, at anode what happens? At anode, CH3 dot plus CO2 is obtained. That CH3 dot will combine with one more CH3 dot to form C2H6. To form respective C2H6. Ethane is obtained as a major product. CH3 dot will combine each other to form C2H6, which is ethane. C2H5 C double bond O minus Na plus electrolysis. You'll get what? C2H5 dot combining with one more molecule of C2H5 dot, it will form N-butane or not? Yes or no?
Yes.
CH3, CH2, CH2, CH3, which is nothing but N-butane. CH3, CH2 dot, CH3, CH2 dot, N-butane is obtained. Look at here. What is the product obtained here? CH2, C double bond O minus. You will get a CH2 dot plus CO2 and CO2. So this will combine with each other to form CH2 double bond CH2, which is nothing but ethene is obtained. Ethene is obtained. Yes or no? And you can think of another way also. CH2 dot molecules. Two such molecules may combine to form CH2, 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 CH2. But cyclobutane will be having ring strain, because of that is unstable. Unstable due to ring strain. Here we will get what? HC double bond C H dot dot. It will combine CH triple bond CH, which is nothing but acetylene. Acetylene is obtained as a major product. In this particular case, sodium malate upon electrolysis will produce acetylene. And is there a possibility to form this species? CH dot double bond CH dot double bond CH dot CH double bond C single bond CH double bond CH. This species can be formed or not?
No, sir.
No, sir.
Because it is anti-aromatic in nature, right?
Anti-aromatic.
anti-aromatic which never be formed. Earlier in the previous case, cyclobutane, there is a possibility. Probability is less, ethene is major, but here it is never found because it is highly unstable. Yes, these are the techniques of producing respective alkanes from the Kolb's electrolysis. The next one is decarboxylation reaction, soda lime decarboxylation. So carboxylic acid or sodium salt of carboxylic acids are heated with soda lime. Soda lime means NaOH in the presence of CaO in the 3:1 ratio. We will be producing what? Manasi, if you take two different types of carboxylic acid, you will get mixture of products. You are not going to expect a single product. Okay.
Okay, sir.
If I take sodium salt of ethanoic acid and propanoic acid, then I'll be getting mixture of products. Again, if you get a mixture of products, you have to do the separation technique like fractional distillation and all. Okay, because boiling point difference of two alkanes will be less than 40 degrees. So that will be again a tedious job. So to get a pure compound, you have to take only one type of carboxylic acid. Soda lime decarboxylation, carboxylic acid or sodium salts of carboxylic acids are heated with soda lime, NaOH and CaO in 3:1 ratio. What is that? Removal of carbon dioxide from carboxylic acid is known as decarboxylation. D means what? Removal. Carboxylation means CO2 has been removed. Removal of CO2 from the carboxylic acid is said to be decarboxylation. And how is that done? CH3 C double bond O minus CH3 COH. If you take salt of carboxylic acid or carboxylic acid, treat with NaOH in the presence of CaO, it will form CH4 plus Na2CO3. What was the mechanistic approach? Can anyone say? Yesterday I have given the hint to you also.
Carbanion.
Carbanion, very good. Okay, so how is that mechanism? How that mechanism can be understood? We'll understand now. R C double bond O minus Na plus. I have taken some sodium salt of carboxylic acid. It will form respect to R C double bond O minus. This R C double bond O minus, this negative charge on oxygen comes into the carbon alkyl group bond, whatever it is there, that electron density is given to R, forming R minus plus C double bond O, C double bond O. This is nothing but your carbanion. This carbanion will now try to pick up the proton. The R minus will try to pick up the proton to form respect to RH. This is what your mechanism is. So how is this proton picked up and how is this carbanion formed? What was the complete mechanism? We will understand now. And what was the rate determining step? All those points we'll understand. Rate determining step is always the formation of carbanion. This is RDS. In the rate determining step, the O minus comes into C double bond moves away. You get CO2 and R minus. This CO2 will also be attacked by OH minus. We'll understand the mechanism completely. So the CO2 we have to remove out and you have to directly connect alkyl group with hydrogen. So what is the complete mechanism, students? You have R, C double bond OH. I have taken some carboxylic acid and I am adding NaOH, right? This NaOH will pick up this proton. It will form respect to R, C double bond O minus. Of course, Na plus and H2O is formed. R, C double bond O minus Na plus H2O. This R, C double bond O minus, R, C double bond O minus will be reacting with, in the presence of NaOH and CaO. Rate determining step, O minus comes into the Cr bond moves away. We have R minus and C double bond O form. This CO2, C double bond O react with OH minus. OH minus tries to attack this particular carbon, pi electron density moves away. You get OH, C double bond O, CO minus. OH, C double bond O, CO minus is going to be formed. And this will have electrostatic force of attraction with Na plus. Here also we have electrostatic force of attraction with Na plus. So we have R minus, Na plus, and we have OH, C double bond O minus Na plus. R minus will try to pick up this proton. This OH electron density will be given to oxygen. So O minus will pick up this Na plus again, forming RH and C double bond O minus Na plus, C double bond again O minus Na plus. What is this? Nothing but CO3 to Na to CO3 or not? This is
Yes,
nothing but Na to CO3. That is CO3 2 minus ion is released out. So mechanism goes in this fashion. Okay, R minus Na plus NaHCO3 is released as RH plus Na2CO3. You have to understand this point carefully. Why I am saying this is the carbon dioxide is not removed in the form of CO2. The CO2 has been converted to CO3 2 minus in the total course of reaction. So NaHCO3 reacts with R minus Na plus to form Na2CO3. To form Na2CO3. Is that clear, students?
yes, sir.
The carbon dioxide, the carbon of respect to carboxylic acid is lost in the form of CO3 2 minus ion, not simply as CO2. It is lost in the form of CO3 2 minus ion. Right? Just a second. In this reaction, carbon ion is intermediate. These are the note points to be noted. Rate of decarboxylation is directly proportional to stability of carbon ion. Because if the carbon ion is the intermediate and if the more stable carbon ion is obtained, so rate of decarboxylation that should be proportional to stability of carbon ion. Product contains one carbon atom less than reactant because carbon is lost in the form of CO3 2 minus. That is why this reaction is used for stepping down in homologous series. That is why this reaction is used in the stepping down of homologous series. And why we are using CaO? CaO is used to keep the NaOH dry. Because if you do not, you can look at the overall reaction course. There is no use of CaO. I'm just attacking OH minus, picking up the proton. It is attacking the electrophilic carbon of CO2. In the total reaction mechanism, is there any CaO involved? There is no CaO, right? The CaO role is only to keep NaOH dry. Why? Because it is highly hygroscopic in nature. It can be reacting with water. So to stop that and making the OH minus react with the respect to carboxylate as, we'll use CaO. Right, students? CaO is used to keep the NaOH dry because it is quite hygroscopic in nature. And one more important point is beta keto acids will undergo decarboxylation by simply heating. No need of soda lime. Why? Beta keto acid, if you take like CH3 C double bond or CH2 C double bond OH, this you can simply heat it. That's it. Upon simple heating only, you will be getting the respective CH3 C double bond or CH2H. This total CO2 is lost in the form of CO3 2 minus, and you will get CH2H. What was the reason for this? CH3 C double bond or CH2H and CO2 is lost. What was the reason for this? If I have a beta keto acid will undergo decarboxylation by simple heating. There is no requirement for soda lime because beta keto acids undergo decarboxylation through a 6-membered cyclic transition stage. Right on that point, beta keto acids will undergo decarboxylation through a 6-membered cyclic transition stage, cyclic TS. And let us understand the mechanism for the same molecule CH3 C double bond O, CH2 C double bond OH, CH3 C double bond O, CH2 C double bond OH. Now understand this point. This C double bond O pi electron density, whatever you have, that is now going to form a new bond. This is now going to form a new bond. This OH electron density is given to this particular carbon. This carbon-carbon single bond electron density is now going to give in this manner. So we have a lot of electronic rearrangements happening. So we'll be having transition state in this manner. CH3C. In the transition state, we can include the bonds which are going to be about to be formed and the bonds which are about to be broken using dotted lines. So I can write CH3C, C double bond O, one bond is present, the other bond is about to be lost. So we have dotted line oxygen. And this OH bond is about to be formed, dotted line hydrogen. This OH bond is about to be broken, dotted line oxygen. This is a CO bond. One bond is already there, the other bond is also formed, about to be formed, C double bond O. This C double bond is undisturbed. And we have the CH2 carbon CH2. This new bond is about to be formed. The old bond is about to be broken. This is nothing but your 6-member TS. 6-member transition state is obtained. How the 6-member states will be present? How the 6-member rings are present? How the 6-member rings are present, students? No idea? Chair form? Yes or no? Chair form, boat form, twist boat, half chair. So this 6-member transition state will also exist in chair form. It is not just the cyclohexane which can exist in chair form. The transition states can also exist in chair form, making the repulsions minimum. So because of that 6-member transition state which can exist in chair form, which will be giving the least repulsions, immediately it will convert to, so this CH3 will be there, this C double bond O new bond form, this carbon double bond CH2, the C double bond O is lost, right, and the COH bond is formed. Along with that, you will form C double bond O, C double bond O. This is nothing but enol. It will tautomerize. It will tautomerize to form CH3, C double bond O, CH3, which is nothing but a keto form. Okay, CH3, C double bond O, CH3 is formed, which is nothing but acetone. So beta keto acids will be simply undergoing decarboxylation by heating. Why? Because they proceed through a 6-member transition stage and not like a carbanion system and all. Not like a carbanion system and all. So let us look at the examples. Compare the rate of decarboxylation in the given compounds. So compound A, so we get what type of carbon ion? CH3, CH2 minus. Compound B, CH2 double bond CH minus. Compound C, CH triple bond C minus. Which will undergo decarboxylation at a greater rate? A, B, C.
C.
Because that carbon ion which is more stable, that is going to be undergoing decarboxylation greatly. So C greater than B, B greater than A. Because more electronegative atom possessing negative charge is more stable. So C, then B, then A. That's the right order. C greater than B greater than A. C greater than B greater than A. That will be the right order because sp hybridized carbon is more electronegative. More electronegative atom possessing negative charge is more stable. So C, B, A. That's the right order. Try to answer this here. CH3, C double bond O, CH2, C double bond OH. Benzene, CH2, C double bond OH. A and B. Compare the rate of decarboxylation. In B, what is the carbon ion formed? B, what is the carbon ion formed? C6H by CH2 minus or not?
Yes, sir.
So which should be greater than A or B?
A, sir.
Why, Faisal?
Quality resonance.
Quality resonance. Quality resonance, you don't get confused, okay? Quality resonance just means on some of the atoms we have negative charge, more electronegative atom possessing negative charge. That is quality. There is no separate meaning at all. Quality resonance means electronegative atom possessing negative charges. But in A, instead of quality resonance, we have to say that beta keto acid. It is a beta keto acid or not?
Yes, sir.
Okay, we have to say it as a beta keto acid. Beta keto acid will produce 6-member transition state. It is not a carbon ion. Okay, beta keto acid, and in B we have C6H5CH2 minus. So A should be greater than B because beta keto acids undergo decarboxylation by simple heating because of 6-member transition states. You don't need to think of this. You should not think like this. Okay, beta keto acids undergo decarboxylation by 6-member transition states, and their rate will be very high. If we have two beta keto acids, then if they are asking the comparison, then you can support the carbon ion acts as a support. Then you have to check out which carbon ion has been having more resonance, that is more stable. So here it should be A greater than B. Compare here, compare rate of decarboxylation in the given compounds. Decarboxylation means in A you will be getting this type of species, CH2 minus NO2. NO2 is electron withdrawing group, NO2 minus M group, CH3, Cl is minus I group, CH3, what is the CH3 group? Plus I or plus H? Plus H we have to write because it is at para position. Here no effect. So we have CH2 minus in every case. So NO2 electron withdrawing groups increase the stability because they are decreasing the charge. Which is withdrawing the electron density greatly? NO2. So A should be greater. And in C, C is also effectively withdrawing the electron density. So after A you have C. In B and D, B is actually donating the electron density because of hyperconjugation, whereas in D no effect. So D will be greater than B. ACDB is the right order. ACDB because electron withdrawing groups remove the negative charge, making it more stable. Electron withdrawing group making the system more stable. Electron donating group making it unstable. Which salt of sodium salt of which acid will be needed for the preparation of propane? Propane you have to prepare. So propane means CH3, CH2, CH3. You get a, if you take A, you get CH2 minus, that picks up the proton. If you take this, you get CH3 minus, that picks up the proton, forms methane here. In a C and D, you will be getting different other compounds, so A will be right. Do this question. C double bond O, C double bond OH upon heating forms A. A upon heating with zinc amalgam in the presence of constant HCl upon heating forms B. What is A and what is B? Can I say it is a beta keto acid? B, because I can write this compound in this manner, right? C double bond OH. This is a functional group. This is alpha carbon. This is beta carbon. On the beta carbon, you have C double bond O. Beta keto acid will undergo decarboxylation immediately. So CO2 is going to be lost. This carbon is going to connect to hydrogen. So you get C double bond O. This treated with zinc amalgam in the presence of constant HCl. What type of reaction is that?
Clemmensen reaction.
Clemmensen's reduction. Clemmensen's reduction. Clemmensen's reduction will try to convert the C double bond O to respect to CH2. So you get B as cyclohexane. B as cyclohexane, A as cyclohexanone plus CO2. Understand here in A, although it is decarboxylation, but it is proceeding through 6-member transition states, you will get a CO2 as a product. But if you do not have beta keto acid where carbon ion is the intermediate, in that case you get a CO3 2 minus as a product. The carbon of carboxylic acid is removed as CO2 in case of beta keto acid, but in the other decarboxylation it will be removed as CO3 2 minus ion. Right. Next one is a preparation of alkanes using Grignard agent. Grignard agent will try to pick up the proton from acidic, try to pick up the proton which is acidic proton. Acidic proton is that proton which is connected to more electronegative atom like nitrogen, oxygen, fluorine, sulfur, chlorine and others. Preparation of Grignard agent. Grignard agent can act as a nucleophile as well as a base. It will act as a base when there is an acidic proton. It will act as a nucleophile when there is no acidic proton. When we have only electrophilic centers, then it will act as nucleophile. If there is an availability of acidic proton, it will act as a base. So Rx plus Mg in the presence of dry ether forms RMgx. CH3Br plus Mg gives CH3MgBr. PHBr plus Mg gives PHMgBr. Grignard agent behaves like base and reacts with compounds containing acidic hydrogen. Grignard agent behaves like a base and reacts with compounds containing acidic hydrogen. RMgx plus ZH. Hydrogen is connected to Z. Z is more electronegative atom. It forms R minus will try to pick up the proton and Mg connected with X and Z. Understand this concepts carefully. Hydrogen should be attached with a carbon, carbon only in some cases, nitrogen, oxygen, sulfur, fluorine, chlorine, bromine, iodine. And these are the cases: HCl, HBr, HOH, that is water, HOR. Hydrogen should be connected with the chlorine, bromine, oxygen, nitrogen, sp hybridized carbon. And we have given the same example, famous example. What is that? This one. In aromatic cases, plus RMgx. R minus picks up this proton to forms this component RH. Carbon should be sp hybridized. In some cases, what are those cases I am reviewing? And sp hybridized carbon, HC triple bond CH plus RMgx. R minus picks up this proton. CH electron density is given to HC triple bond C minus plus RH. RH is nothing but your alkane. Is that clear, students? Yes, please.
Sir, in MgX, if X is more electronegative, then how does R have a negative charge?
Does R is connected to magnesium or not? The CH3 MgF, if you take among carbon and magnesium, which has more electronegativity? Magnesium is a metal, electropositive in nature.
Yes,
The alkyl group is connected with magnesium. So alkyl group, which is just made of carbon and hydrogen, that is withdrawing the electron density, right? So carbon should be having negative charge. It should be behaving as a base or nucleophile. Okay.
Okay, yes, sir.
So pH MgBr plus water. Water means you can say hydrogen connected with OH, hydrogen connected with oxygen. So pH minus tries to pick up the proton. What is the product obtained here? pH minus picks up the proton and you'll get PHH plus MgOHBr. That is benzene plus MgBrOH is obtained. Second case, pH minus, it will be connecting with a D2O. D2O means deuterium connected with OD. C6H5 minus picks up the deuterium and it will form PHH and MgBrOD instead of OH. CH3 MgBr plus C2H5OH. C2H5OH means you can write as hydrogen connected with oxygen, oxygen connected with C2H5. CH3 minus picks up the proton. So wherever there is an acidic proton, you should always think of Grignard agent as a base. CH3 minus picks up the proton, forms what? Forms CH3 minus picking up the proton, CH4 is formed. Along with that, you will get MgBrOC2H5. CH3H plus MgBrOC2H5. All these reactions clear, students?
Yes, sir.
Yes, right. And from metal carbides, this is the last type of reaction by hydrolysis. Mechanism of these reactions are not required. CH4 can be obtained by hydrolysis of beryllium or aluminum carbides. Al4C3 plus 12H2 upon heating produces AlOH taken thrice plus 3CH4. Be2C plus 4H2O gives BeOH taken twice plus CH4. So these are the ways actually where the metal carbides were heated in the presence of water. Yes or no? Hydrolysis of metal carbides, that is actually producing your respective methane. These are the different methods of preparations of alkanes. What are the methods? Reduction, Woods reaction, Woods-Fittig reaction. Then you have Grignard agent. Then you have decarboxylation and Kolb's electrolysis. Yes or no? These are the different ways to actually prepare your respective alkanes. Any other method we missed out? Clemenson's reduction, Wolff-Kishner reduction, all they are included in the reductions only. Yes or no? So these are the different ways to actually prepare the alkane, students. And then comes the properties, physical properties and chemical properties. If you look at physical properties like solubility, alkanes being non-polar are insoluble in water but soluble in non-polar solvents. Like you can say like dissolves in like. This is always applicable. Yes or no? So alkanes are non-polar. Alkanes are non-polar. If you take a solvent which is non-polar, the non-polar alkane molecules will develop new interactions with the non-polar solvent molecules. That can happen. But if you take solvent which is polar, the polar solvent molecules have electrostatic force of attraction within themselves. So alkane cannot develop new interaction greatly. So alkanes being non-polar, they are insoluble in water because water is polar in nature. But soluble in non-polar solvent like benzene and CCl4. They are soluble in non-polar solvents like benzene and CCl4. And if you look at boiling points, boiling point is directly proportional to what? Molecular weight. If you are talking about alkane, different types of alkane, methane, ethane, propane, butane and all. Increase in the molecular weight increases van der Waals force of attraction, as molecular weight is directly proportional to van der Waals force of attraction. Van der Waals force of attraction. Yes or no? So boiling point is directly proportional to molecular weight. As molecular weight increases, van der Waals force of attraction will be increased. And if we have same alkanes, isomeric alkanes, in that case, branching will be affecting. If you have more branching, what happens? Like if you have all the 6 carbon atoms involved in this manner, all the 6 carbons, and we can also have the other scenario like this, and we can have other scenario in this fashion. Like 5 carbons you take, N-pentane, isopentane, neopentane. Whenever you are trying to increase the branching, what is going to happen, students? If you are trying to increase the branching, can I say the molecule is acquiring more of spherical shape? Yes or no?
Yes.
If the molecule is acquiring more of spherical shape, what happens to the intermolecular force of attractions? They will be decreased or not? Because surface is decreased. Because surface area is also going to be decreased or not? If whenever you have more branching, the molecule assumes to be, it is acquiring a shape similar to spherical. In that case, its surface contact will be decreased. In that case, intermolecular force of attraction decreases. So greater the branching, lesser will be the boiling point. Boiling point is inversely proportional to branching and directly proportional to molecular weight. If a molecular weight is same, then only you have to look at branching. If a molecular weight is differed, then higher the molecular weight, higher will be the boiling point. So we can say N-butane, N-pentane, N-hexane, which will have higher boiling point. Simply I can say N-pentane, N-hexane will have highest, then N-pentane, then N-butane, based on boiling point, based on molecular weight. N-pentane, isopentane, neopentane, which will have higher?
N-pentane.
Pentane.
N-pentane, because branching is increased. With increase in branching, the boiling point decreases. Why? Because intermolecular force of attractions, they are going to be decreasing. You can see the figures. Okay, so how the molecule shape, you can see this dark line or not, the black color, whatever I have mentioned.
Yes, sir.
Yes or no? So you can see in neopentane we are acquiring the spherical shape. Because of that, intermolecular force of attraction decreases. Write down one point if you want. With increase in branching, with increase in branching, the alkane acquires, the alkanes acquires a spherical shape, and thus there is a decrease in intermolecular force of attractions. Types of chemical reactions, like we have discussed different types like addition reactions, elimination reactions, and we can also have substitution reactions, replacement, and we can also have rearrangement reactions. Yes or no? So different types of chemical reactions are there. Alkanes will undergo what type of chemical reactions majorly? As discussed earlier, can anyone say what are the different types of reactions or chemical reactions undergone by alkanes?
Free radical substitution.
Free radical substitution reactions. Very good. Okay, these are the general reactions. In the GOC2 also we have studied addition reaction means electrophilic addition reactions, free radical addition reaction, nucleophilic addition reaction we have discussed. Elimination E1 and E2 we have discussed. Substitution, electrophilic substitution, free radical substitution, nucleophilic substitution reactions, rearrangements, tautomerism and isomerism. These are the different types of reactions. Can anyone say electrophilic addition reactions undergone by which compounds majorly? As we have already discussed. Electrophilic addition reactions.
Alkenes.
Alkynes, very good. Free radical additions. Example, you can take alkane in the presence of HBr addition. HBr peroxide, H2O2. Nucleophilic additions.
Carbonyl compound.
Carbonyls, very good. E1 and E2. Alkyl halides treated with alcoholic OH. General example we are writing. Alkyl halides treated with the alcoholic OH, E1 and E2. Electrophilic substitution reactions given by
Aromatic
aromatic compounds. Free radical substitution reactions. Alkanes. Nucleophilic substitution reactions. SN1, SN2, SNI. Tautomerism. Include the bread stool as well. Ketoenol and bread stool. And isomerization reactions. In alkanes also we have some type of isomerization reactions. Like you can say this reaction N-butane, CH3, CH2, CH2Cl treated with AlCl3 in the presence of HCl at high temperature. It forms isobutane. The rearrangement is going to happen. It is an example of rearrangement reaction only. Like that, we have studied different types of reactions. So now in alkane, as we are saying, the alkanes are going to be undergoing free radical substitution reactions. The characteristic reaction of alkane is free radical substitution reaction. In the free radical substitution reaction, what is the RDS, students? What is the rate determining step? RDS.
chain propagation.
Yeah, in the chain propagation, a lot of steps, Satika. What is that step?
Free radical form.
Free abstraction of hydrogen to form a free radical. Very good. So substitution reaction, halogenation if you take RH alkane plus X2 in the presence of high temperature or diffuse sunlight or UV or 573 to 773 Kelvin. In all these cases, you get a free radical path. You will be generating Rx plus Hx. Rx plus Hx. Let us go with the mechanistic approach. Halogenation of alkane will have three main steps: chain initiation, chain propagation, chain termination. In the chain initiation, the halide radicals are obtained. In the chain propagation, the halogen radical will try to pick up the hydrogen to form alkane radical, alkyl radical. That alkyl radical will be combining with the halogen radical to form haloalkanes. They can combine with each other to form higher alkanes. Like that, mixture of products can be expected. CH4 plus Cl2 gives rise to CH3Cl plus HCl in the presence of sunlight. Mechanistic approach. Step 1, chain initiation step. Cl2 molecule, upon treating with H mu, it forms a Cl dot, chlorine free radical. Chain propagation step. Cl dot will try to pick up the hydrogen. This is nothing but RDS, rate determining step. CH3 dot plus HCl. CH3 dot will react with one more Cl2 to form CH3Cl and Cl dot. Chain termination. The chlorine free radicals will combine with each other to form Cl2. The methyl free radical can combine with Cl dot to form CH3Cl. And two methyl radicals can also combine to form higher alkanes. So in the free radical substitution reactions of alkanes, there is a high possibility for the formation of mixture of products. That is why whatever the haloalkane you are supposed to prepare, you are not going to choose this path. Is that clear, students? Is everything clear so far?
Yes, sir.
sir.
So if I have given, since you have understood the rate determining step is the formation of respective free radical. So based on the stabilities of free radical, you can compare which will have greater rate towards the free radical substitution reaction and all. And this free radical substitution reaction is going to be regioselective. Regioselective means what? That means the hydrogen is picked from which region, that decides the stability of carbon free radical. So reactivity order of halogens F2 greater, then Cl2, then Br2, then I2. F2 is more reactive, then Cl2, then Br2, then I2. But we will discuss mainly about chlorination and bromination, because fluorination is very explosive in nature, iodination is very slow, and iodination is also reversible in nature. In this reaction, intermediate formed is carbon free radical. RDS of this step is first step of chain propagation, that is abstraction of hydrogen to form a free radical. Abstraction of hydrogen to form free radical. Rate of halogenation is directly proportional to stability of free radical. That is sure, because more stable free radical if you are getting, more will be the rate of respect to halogenation. Right? The order of reactivity of hydrogen towards free radical halogenation is, if we take primary, secondary, tertiary, allylic, benzylic, which will be having greater rate? Here you will get CH3, CH2 dot. Here you will get CH3, CH dot, CH3. Here you will get CH3, C dot, CH3, CH3. Here you will get CH2 double bond, CH, CH2 dot. Here you will get PH, CH2 dot. Yes or no? So which free radical is more stable? Benzylic, then allylic, then tertiary, then secondary, then primary. Yes or no? Your order already given. So increasing rate of reactivity towards halogen in the presence of sunlight, because this is the order of stability. What is the order of stability of carbocation?
Tertiary greater than secondary.
Like benzylic and tertiary, if I given benzylic and tertiary, which will have greater? Tertiary means tertiary butyl. Which will have greater? Benzylic and tertiary butyl, we have tertiary butyl greater than benzylic. Okay, this is an exception case. Based on rates, we can say tertiary butyl, only tertiary butyl, not we are saying all tertiary, only CH3C, CH3, CH3 plus. Due to hyperconjugation of 9 alpha hydrogens, the tertiary butyl will be having more stability when compared to your respective benzylic carbocation. If you go with the carbocations, there's an exception. If you go with the free radical, that is not an exception. Benzylic is greater when compared to tertiary. To avoid polyhalogenation, alkane should be taken in excess. If you have taken excess amount of alkane, obviously all the alkane molecules want to react. If only one molecule is there, after the monohalogenation, the same molecule may undergo dihalogenation. The same will undergo trihalogenation, the same will undergo tetrahalogenation. But if you take more number of alkane molecules, every alkane will have a tendency to undergo monohalogenation first, because dihalogenation, trihalogenation, tetrahalogenation will have more number of halogen atoms, which will repel greatly. Because of that repulsion, we will be having unstable nature. CH4 excess, if you take, you will get CH3Cl. If you take CH4 plus Cl2 excess, then you will get CCl4. There's a difference. If you take more halogen, you will get a polyhalogenate product as major. If you take more amount of alkane, you will get alkane will be the major, that is excess. CH4 plus Cl2 gives rise to CH3Cl plus HCl in the presence of H mu. CH3Cl again treated with Cl2 in the presence of H mu forms CH2Cl2 and HCl. CH2Cl2 treated with Cl2 in the presence of H mu forms CHCl3 and HCl. CHCl3 treated with Cl2 in the presence of H mu forms CCl4 and HCl. So this is a sequence of steps. Everyone got this or not? This was a sequence of steps. Fluorination is explosive in nature and should be carried out in the presence of inert gas like N2. It is explosive in nature, so it is going to release lot of heat. So to reduce that heat, we have to use a coolant like N2. Fluorination can take place in dark too. Bromine is less reactive than chlorine, so generally requires high temperature for bromine. Iodination is reversible, so it has to be carried out in the presence of oxidizing agents like HiO3 and HNO3. CH4 plus I2 will form CH3I plus HI. HiO3 will react with HI to form I2 and H2O. Okay, whatever the HI is there, that will be taken up by HNO3 and again I2 is formed. So if you take HiO3 and HNO3, then only the HI will be removed and again forms I2 and again the forward reaction will be more. If you don't remove the HI using oxidizing agents, then the reverse reaction, that is CH3I plus HI, will react with each other to form CH4 and I2 back. Okay, iodination is reversible, fluorination is explosive. Why fluorination is explosive? Because fluorine-fluorine bond is weakest bond. Why? Because of more repulsions. That is why whenever you are doing fluorination, you have to use a coolant like N2 gas. Chlorination and bromination. Bromination is less reactive than chlorination. Because of that, high temperature is required for bromination. Iodination is reversible, so that is why you have to use oxidizing agents. Right, students? Let us try to solve examples. Everyone understood these points or not? What type of products are obtained? How are they obtained so far?
Yes, sir.
Yes. Try to answer this question. CH3, CH2, CH2, CH3 plus Br2 in the presence of H mu, 127 degrees Celsius. CH3, CH2, CH2, CH3 plus Br2 in the presence of H mu, 127 degrees Celsius. What will happen? So you have this particular carbon, this carbon, these terminal carbons are same. These two center carbons are similar. So which hydrogen is going to be replaced? So if this hydrogen is removed, you will be getting two type of radicals, CH3, CH dot, CH2, CH3 plus CH3, CH2, CH2, CH2 dot. This is primary free radical, this is secondary free radical. Secondary free radical is more stable. Because secondary free radical is more stable, it will be forming major protas 2-bromo butane. Yes or no? 2-bromo butane is going to be the major, 1-bromo butane, that is going to be the minor. How many structural monochloro products or derivatives are possible for the given compounds? CH3, CH2, CH3 plus Cl2 in the presence of H mu. How many structural monochloro products they are asking? What are the compounds you can expect? CH3, CH2, CH2, Cl plus CH3, CHCl, CH3. That is how many structural products you obtain? How many structural monochloro products or derivatives are possible? 2. What are those? These 1-chloropropane and 2-chloropropane. How many structural monochloro products or derivatives are possible for this compound N-butane?
2.
2. Yes or no? So again 1-chlorobutane and 2-chlorobutane. CH3, CHCl, CH2, CH3, Cl, CH2, CH2, CH3. 2. How many structural monochloro products are possible in this compound? How many different types of hydrogens are available? That you have to check out. Yes or no? How many structural monochloro products or derivatives are possible for this compound? You will get CH3, CH, CH3, CH2Cl, and CH3, CCl, CH3, CH3. So again 2, right? Is there any other possibility? Because these 3 methyls are same. So picking hydrogen from all those 3 carbons is going to be resulting the same compound. CH3, CH, CH3, CH2Cl, CH3, CCl, CH3, CH3. How many structural monochloride products are possible in this compound?
One.
Only one, that is CH3, CH, CH2Cl, CH3, CH3. Because only one type of hydrogen is possible. What is compound A, B, and C? What is compound A? A is going to be respect to cyclohexane because decarboxylation we are doing, and B, cyclohexane read with Cl2 in the presence of H mu. Only one type of hydrogen is there, so monohalogenation we are restricting to. Sodium in the presence of diether, so it will form Mg. Sodium in the presence of diether, that is nothing but your Woods reaction, right? Woods reaction will lead to the formation of
Biphenyl.
not a phenyl, bicyclohexyl.
Bicycles.
Yes. A will be a cyclohexane, and then you have chlorine substitute on cyclohexane, then you have bicyclohexyl, that is going to be a C. Is everything clear, students, so far?
Yes, sir.
sir.
Yes, right. So then you can have the next set of reactions as well. So next set of reactions, allylic and benzylic hydrogens, which are allylic, which are benzylic. And allylic and benzylic, I have told you two things. What are the two reagents where you can do allylic substitution and benzylic substitution? NBS, NCS, N-bromosuccinimide, N-chlorosuccinimide. The sp2 carbons of an alkane are called vinylic carbons. An sp3 carbon that is adjacent to vinylic carbon is called allylic carbon. A hydrogen bonded to vinylic carbon is called vinylic hydrogen, and the hydrogen bonded to allylic carbon is called allylic hydrogen. So R, CH2, CH double bond, CH, CH2R. So these carbons are vinylic carbons, these carbons are allylic carbons, and the hydrogens connected to vinylic carbons are vinylic hydrogens. Hydrogens connected to allylic carbons are allylic hydrogens. Calculate the total number of allylic hydrogens in this following compound. Total number of allylic hydrogens in this particular compound, whatever given to you.
7.
7.
Yes or no? So allylic means this is allylic carbon. Here we have 3. This is also allylic. Here we have 2. This is also allylic. Here we have 2. So 7 allylic hydrogens are there. Right? Allylic and benzylic substitution reaction, that is free radical substitution reaction, they will be happening in NBS and NCS. Reagents used for halogenation at allylic and benzylic positions are NBS, N-bromosuccinimide, NCS, N-chlorosuccinimide. It is an example of free radical substitution reaction. So NBS will have this structure, C double bond O, C double bond O, NBR. This is your NBS. N-chlorosuccinimide means if you have chlorine, you'll say N-chlorosuccinimide. It is also proceeding with the free radical path. So what happens in the case of this particular reaction? Cyclohexene treated with a H mu in the presence of NBS. What happens, students?
Bromine is added to the allyl.
Bromine is going to be added to the allylic carbon. So we'll have simply bromine connected here because allylic free radical is going to be more stable. Here what will happen? Like I'll give numbering A, B. Which carbon is going to be substituted by bromine? Out of A and B carbon atoms, which carbon is going to be substituted or attached by bromine? Obviously, carbon A, because it is going to be benzylic. So bromine is going to be added here. Allylic and benzylic substitution will happen. You get this type of free radical that will react with NBS to form bromine substituted to the benzylic position. Which of the following is more reactive towards N-bromosuccinimide, NBS? Which of the
B.
following is more reactive?
B.
B or A?
B.
B.
Why?
Because it will show resonance as well as hyperconjugation.
Very good. In A, we have only benzylic free radical, but in B, we have CH dot CH3. So both resonance and hyperconjugation. Resonance plus hyperconjugation. Because of that, B is going to be more stable. Because of that, B will have greater rate towards nucleophilic, towards free radical substitution reaction, that is towards NBS. Only resonance in benzylic free radical, but whereas in the second type of free radical, whatever you got, there you have resonance plus hyperconjugation. Right, students? Everything clear so far or not?
Yes, sir.
Yes, right. So next point is next combustion reactions. So we have some set of reactions whose mechanisms are not required, and we have to remember the reactions also. So generally, if you try to do the combustion of alkane or any hydrocarbon, what is the general example? CXHY plus X plus Y by 4 O2 gives rise to XCO2 plus Y by 2 H2O. CXHY plus X plus Y by 4 O2 gives rise to XCO2 plus Y by 2 H2O. This is nothing but your complete combustion reaction of any hydrocarbon of molecular formula CXHY. Alkanes on heating in the presence of excess of air or dioxin are completely oxidized to carbon dioxide and water with the evolution of large amount of heat. With the evolution of large amount of heat. But there is a possibility of incomplete combustion also. In the incomplete combustion of alkane, incomplete combustion will happen whenever we do not have a sufficient amount of air or dioxin. Then you don't have the formation of carbon dioxide, whereas carbon black is going to be formed. So if I treat methane with oxygen in the incomplete combustion, then you will get carbon solid plus 2 H2O only. During incomplete combustion of alkanes, with insufficient amount of air or dioxin, carbon black is formed. CH4 plus O2 incomplete combustion gives C solid plus 2 H2O. Is that clear or not? Complete combustion means the carbon is going to be converted to respective carbon dioxide. In the incomplete combustion of methane, you will produce respective carbon black. Along with this incomplete combustion and complete combustion, there are some controlled combustion reactions. Like they are going to be decided with the type of catalyst we have used. Like if I do the conversion of CH4 to respective methanol, so CH4 plus O2, if you treat this with a copper at a very high temperature, like 300 degrees Celsius or 570 or 530 Kelvin, around 523 to 543 Kelvin, yes or no? And a very high pressure like 100 atmosphere, it will form what? CH4 plus O2. This is controlled combustion, it will form CH3OH. If I treat methane with a oxygen in the presence of copper catalyst at very high temperature and pressure, it will form methanol. You treat CH4 plus O2 in the presence of molybdenum oxide, MO2O3. Molybdenum oxide at very high temperature, it will form what type of sub product? Methanol is obtained, HC double bond OH. If you take ethane and treat with ethane, CH3CH3 and heat with manganese acetate, MnCH3COO taken twice, it will form what? Same oxidation. It will form ethanoic acid. You will get CH3, C double bond OH. So these are all the controlled oxidation reactions. Controlled combustion reactions. And if you take any tertiary alkane, treat with KMNO4. Alkanes, if they have tertiary hydrogen like CH3, CH, CCH3, CCH3, treated with KMNO4, it will form CH3, C, CH3, C, CH3, and this tertiary hydrogen will be converted to respect to COH. So we'll have alkanes having tertiary hydrogen will be forming tertiary alcohols. You have to remember these conditions. Under different types of catalysts, we are getting different types of products. Alkanes with a tertiary hydrogen, will be reacting with KMnO4 to form tertiary alcohol. Is that clear, students?
Yes, sir.
Yes.
The first reaction CXH5 plus X plus Y by 4 O2 gives rise to XeO2 plus Y by 2 H2O is complete combustion. And this reaction is incomplete combustion. Incomplete combustion produces carbon black, whereas in the controlled combustion, we'll be having different other sets of reactions. Right? Yeah, this is what I'm talking about. Controlled oxidation or controlled combustion, you can take. In the controlled oxidation, you will be having methane converting into carbonyl in the presence of copper at high temperature and pressure. Molybdenum oxide, methanol is obtained. Methanol, all means aldehyde. Methanol means alcohol. In the presence of molybdenum oxide, you will get a methanol or formaldehyde. In the presence of manganese acetate, you get ethanoic acid. And in the presence of KMnO4 oxidation, tertiary hydrogens present in the alkane, they will form respective tertiary alcohols. Alkanes having tertiary hydrogen atom are oxidized by KMnO4 or oxidized by KMnO4. Is that clear or not? The same reactions we have discussed. Isomerization reaction. Isomerization reaction, what is the example I have given earlier?
AlCl3 in presence.
Yeah, AlCl3 in presence of HCl treated with a alkane to form respective isomeric alkane. Unbranched chain alkanes, like whatever the initial alkane you are taking, that should be unbranched. Unbranched chain alkanes on heating with AlCl3 and HCl, they will be converted into branched chain alkanes, like N-butane to isobutane. N-butane will be converted to isobutane, and this reaction mechanism proceeds through rearrangement. Okay, the mechanism of this reaction involves a rearrangement. As carbocation is formed, as carbocation is the intermediate. You may ask it out, sir, how come carbocation is formed? Because of high temperature, the CH bonds are going to be cleaved, and you will be generating CH3, CH2. CH2 is going to be converted to CH plus, CH3, CH plus, CH2, CH3. That will undergo methyl shift to form respective more stable carbocation. Yes or no? In that way, you will be generating the isobutane. The N-butane to isobutane, the conversion is happening through rearrangements. And you can have this rearrangement CH3, CH plus, CH2, CH3. Methyl shift can occur, forming CH3, CH, CH3, CH2 plus. Again, hydride shift can occur, forming CH3, C, CH3, CH3 plus, and forms a respective hydrogen is going to be attacked now, forming CH3, CH, CH3, CH3. So this is the compound. Like that, rearrangements are going to be included in this particular isomerization reaction. Aromatization reaction. Aromatization reaction means what? Can anyone say? Aromatization reactions. Yes, please.
Sir, alkyne to benzene.
Alkyne to benzene.
Yes, sir, like in presence of iron. No?
Alkyne to benzene or alkane to benzene? Alkyne to benzene is red hot copper tube, right?
Yes, sir. Is there alkane? Sorry,
Alkyne
got
acetylene we
confused.
take.
Sorry,
You are
sorry, got
saying about
confused.
this reaction. CH triple bond CH, CH triple bond CH, CH triple bond CH, red hot copper tube.
Yes, sir.
Okay, but here these are chemical reactions of alkanes, right? We are trying to start with alkane, not alkyne.
Sorry,
Okay.
sir. Sorry. Yeah.
Nothing to be sorry. Okay, so let us start with the aromatization. So N-alkanes having 6 or more carbon atoms. If we have an N-alkane having 6 or more carbon atoms, they upon heating to 500 degrees Celsius, at a 10 to 20 atmospheric pressure in the presence of oxides of vanadium or molybdenum or chromium supported over alumina. I can take chromium oxide in Al2O3, Cr2O3 in Al2O3, or V2O5 L2O3, or MO2O3 and L2O3. That will result in the formation of aromatic hydrocarbons. And the mechanism is not required. That includes the breaking of the CC bonds as well if required. And formation of pi bonds is going to happen. These all reactions will happen at high temperatures. If you take a N-hexane, CH3, CH2, 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 CH3, treated with Cr2O3 in the presence of Al2O3 at 500 degrees Celsius, forms respective benzene, and the CH bonds are cleaved and the H2 molecules are going to be formed, 4H2. If you take N-heptane, CH3, CH2 taken 5 CH3, treated with a oxide of chromium supported over alumina at high temperature, forms toluene. You will always get the substituted benzene only. Benzene or substituted benzene products, aromatic compounds are going to be formed. If you take 8 carbon atoms, what will happen? CH3, CH2 taken 6 CH3. In that case, again you will get ethyl benzene. Yes or no? In that case, again you are going to get ethyl benzene, and you can take oxides of molybdenum MO2O3 or MO2O3 or chromium or vanadium V2O5 in Al2O3 supported over alumina. And these reactions mechanism not required. They include the cleavage of CH bonds. That is why very high temperature is required as well. Right, students? Is that clear or not? So free radical substitution reactions, combustion, incomplete combustion, controlled oxidation, isomerization, aromatization, and we do have other reactions like reaction of alkane with a steam as well as pyrolysis. Pyrolysis, can anyone say? These alkanes are highly unstable, right? That is why they are not going to undergo different types of reactions, because they are already, alkanes are highly stable, right? That is why they are not going to undergo different types of reactions. Different types of reactions are not going to, just a second. To try to solve this particular reaction, students. Okay, think of this. I'll be back in 5 minutes. All of you try to solve this question. Okay, I'll give one question to you. Try to solve this question. Okay, I'll be back in 5 minutes. I'm sorry for the delay, students. So everyone there, right?
Yes, sir.
Yes,
Yes,
sir.
sir.
That's good.
Yes.
So this is what aromatization reaction is, and then comes the pyrolysis. We'll discuss this reaction. Anyone got the answer, right answer for this particular question? We'll discuss the same reaction in the next topic, that is alkenes. It is an alkene given formation of alkenes, dehydration reactions. Dehydration of alcohols will lead to the formation of alkene. How that can be done, we'll be discussing in the next class. Next to pyrolysis. When alkanes are heated to 500 to 700 degrees Celsius, then they are decomposed into lower hydrocarbons. Liquid hydrocarbon is converted into gaseous hydrocarbon. Why? Because the temperature is high, the conversion of liquid hydrocarbon to gaseous hydrocarbon will occur. This decomposition is known as pyrolysis or cracking. It involves free radical elimination because always the CH bonds are only present in the respective alkanes. So the CH bond cleavage will only be forming respective free radicals. So alkane upon heating will produce alkane plus lower alkanes plus H2. CH3, CH2, CH3 upon heating forms CH3, CH double bond CH2 plus CH2 double bond CH2 plus CH3 single bond CH3 plus CH4 plus H2. That means alkane of higher molecular weight, they will be converted to respective alkenes. Along with that, lower alkanes are also formed. Along with that, H2 is also formed. You can understand or read the statement is again. Liquid hydrocarbon is converted into gaseous hydrocarbon. That means that hydrocarbon where the molecular weight is high, if the molecular weight is high, its intermolecular force of attraction would be high, then its liquefaction tendency is high. The heavier hydrocarbons will be present in the liquid state, whereas the lower will be present in the gaseous state. So from the heavier hydrocarbon, we are getting lower hydrocarbons. That is why the alkanes are going to be forming respective alkenes and lower alkanes. Right? This all is happening because of high temperature. If temperature is not maintained high, the bond breaking will not happen. We will not be forming the lower alkanes. And the last type of reaction is reaction with the steam. So if you take methane, methane reacts with steam at 1273 Kelvin. You have to remember the condition in the presence of a nickel catalyst to form carbon monoxide and dihydrogen. This method is used for the industrial preparation of hydrogen gas. What is this reaction also called as?
Syngas reaction.
Yes or no? Syngas, synthesis gas, we will be having different types in the hydrogen and its compounds. So CO plus H2, that is actually prepared. H2 gas is obtained along with the carbon monoxide. Whenever you try to heat methane heated in the presence of nickel at a very high temperature and steam, it will form mixture of carbon monoxide and H2. This is also a method of preparation of H2 gas from heating methane. Right, students? So these are the different types of reactions of alkanes and all. So next topic is alkenes. Alkenes will have again same methods of preparation, physical properties, as well as chemical properties. So we'll start with the methods of preparation, physical properties and chemical properties of alkenes in the next class, so that the continuation discussion can be quite good. Okay, fine. Thank you all everyone. Bye.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Sir, tomorrow we are having class.
Yes, tomorrow all of you have to join at the correct time. So whatever the time mentioned in the portal, you have to join. We'll be discussing solutions chapter. Okay. And from the in the weekdays, whatever the discussion we are continuing, we'll do that. Only on Saturdays, we'll discuss that chapter, specified chapters, whatever they have been mentioned. Okay.
Okay, sir. Thank you.
Okay, fine. Fine.
Thanks.
Thank you all.